Welcome to the 8.2 notes. First things first, make sure you have this piece of paper in front of you. Before we get into the specifics of an ellipse, which is today's lesson, we are going to watch a quick video about what exactly an ellipse is.
Imagine you're standing at one end of a large room and your friend is at the other end. You whisper something, barely audible to the person standing next to you. But your friend can clearly hear what you said. How amazing this would be, right? Is this possible? What do you think? Well, this magical thing is possible if the ceiling of the room is spherically shaped like an ellipse. This shape, which looks like a stretched circle, is what makes the whispering magic possible. If the ceiling of the room is elliptical in shape, technically semi-elliptical here, then there are two special points in the room where you and your friend can stand. If one of you whispers something, then all the sound waves get reflected from the elliptical ceiling towards the other person. So as the sound waves from one point get reflected and focused onto the other point, your friend can hear your whisper. This works the other way around as well. If your friend whispers something, you will be able to hear clearly as well. Based on this reflective property of ellipse, many rooms called whispering galleries have been constructed. For example, there's one at the Grand Central Terminal in New York City. Isn't this shape interesting? Each of these two special points of the ellipse is referred to as focus. And together, they're called the foci of the ellipse. Wait, there's more. Elliptical shapes even play a role in a medical device called the lithotripter. Due to its reflective property, it's used to break the kidney stones. High-frequency shock waves are generated at one focus of the elliptical-shaped reflector, which gets concentrated at another focus point where the kidney stones are positioned. And this helps in breaking the kidney stones.
Now that we know what an ellipse is, let's talk about some of the terms we need to know in order to graph them. Today our job will be to graph them. Tomorrow we will discuss how to write the equations. An ellipse has two axes, a major axis, which is the longer axis of symmetry, and a minor axis, which is the shorter axis of symmetry. The center, just like with a circle, is going to be wherever the major axis and the minor axis intersect. Then, an ellipse is going to have vertices and co-vertices, instead of just endpoints like a circle, because we have to know whether they're on the longer or the shorter side. The vertices are going to be the endpoints of the major axis. Or they are the ones that are further away. The co-vertices are going to be the endpoints of the minor axis. Keeping in mind that the major one is longer, the minor one is shorter. Then there are going to be two versions of the standard form or the equation for an ellipse. A horizontal ellipse is going to be one that goes side to side like this. A vertical ellipse is going to be one that goes more up and down like this. So the major axis determines whether it's horizontal or vertical. For a horizontal ellipse, you're going to have x minus h squared and y minus k squared, just like we did in a circle. And it equals 1 on the other side. But instead of having the radius squared over there, it's sort of like x and y each get their own radius, since an ellipse is longer on one side than it is the other. So underneath x, we are going to put a squared, and underneath y, we are going to put b squared, where a is sort of like the radius for the x direction, and b is the radius for the y direction. The only thing that changes for a vertical ellipse is a is always going to be the longer side. So when the vertical ellipse occurs, a squared is underneath y, and b squared is underneath x. So a and b sort of just switch spots when you go from a vertical to a horizontal. But I'm not going to leave that there because it kind of makes it look messy. The center, just like with a circle, is going to be at H, K. And the vertices are always going to be along the major axis, which is longer. They are A units away from the center. So the vertices are on the X part of a horizontal and the Y part of a vertical ellipse. The co-vertices are B units away from the center along the minor axis because it is shorter. So the vertices are always longer and the co-vertices are always shorter. So whichever one has a bigger denominator, that's where the vertices go. Whichever one has a smaller denominator, that's where the co-vertices go. And then we're going to learn about the foci. The foci, or two focus points that plural, are going to be C units away from the center. But for the foci of an ellipse, C squared is going to equal A squared minus B squared. It's kind of like the Pythagorean theorem, but you have to be very careful because you will notice that I wrote minus right there, not a plus. So you'll have to subtract the squares of A and B. Remembering that A squared and B squared are just the denominators, so you'll basically subtract the denominators, okay? So, as we go into this, the center of this first one, because there are no numbers here next to X or next to Y, the center is going to be at 0, 0. So no number at all means that there is a 0. Then we are going to skip the foci for just a second and move straight onto the vertices. Now, Y has a bigger number underneath, so these are going to be the number, this is going to be the distance for the vertices. This means that the vertices are 6 units away. The fact that the other denominator is 4, and the fact that the square root of 4 is 2, means that the co-vertices are 2 units away. And then the last part is, since this co-vertice one that I just wrote is underneath X, that goes along the x-axis, and the vertices go along the y-axis. So if I put my center at 0, 0, right here, I need to count 6 units for the y. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Those are my vertices. Those are the points 0, 6 and 0, -6. For my co-vertices, I need to go 2 units away, left and right, which is 2, 0 and -2, 0. Then I just simply draw my ellipse through those points. And that's it. Now, that is the main focus of the ellipse, or concentration of the ellipse. We do still need to find the foci. For the foci, c squared equals a squared minus b squared. A squared is 36, b squared is 4, so c squared has to be 32. Then I just do the square root on both sides, and I get the square root of 32, which, pulling out my handy dandy calculator, square root of 32 is approximately 5.7. Now, this is the tough part of the foci, is that 5.7 has to be along the same direction as my vertices, which in this case was y. So this is going to be in the y direction since y had a bigger number underneath. So I take my center and I add and subtract 5.7 to the y part of the point, which gives me 0, 5.7 and 0, negative 5.7. I'm adding it to the y part of my point because it was the y-axis that was the major axis. Then I put 2 points at 0, 5.7 and 0, negative 5.7. Now 5.7 is pretty darn close to 6, so it's going to be like right here and right here. And that's the graph of my ellipse with the foci. Let's try another one because I know that that one can be a little overwhelming with those decimals there at the end. So I want to show you one more time how it works because sometimes the second time just makes more sense. But I am setting up the screen so you can still see the answers to the foci over there on the left. All right, so this one's a little tougher because my center actually has numbers. The x part is going to turn into -1, and the y part is going to be +2. Remembering that because in our formula they are subtracted, we have to always flip them. Then the bigger number is 49, so my vertices are going to be along the x-axis, so 7 units away along the x, because the square root of 49 is 7. So I go to the point -1, 2, and then I'm going to count to the left and to the right 7 units. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Then I'm going to do kind of the same thing for y, except it has a 9 underneath. So my co-vertices are going to be square root of 9 is 3 units away along the y-axis because that one's underneath the y. So 3 and 3. Now that I have them all drawn, my vertices are at the points -8, 2 and 6, 2. And my co-vertices are at -1, 5 and -1, -1. Before I move on to the foci this time, I'm going to pause and say one thing. If you focus on the x part of the center and you add 7 and subtract 7, you'll get the x values of the vertices. The y value stays the same because you're only changing the x since the vertices are along the x-axis. The co-vertices are going to be 3 units away, so you're going to add or subtract 3 to get the y part. That's just an easy way of knowing if your points are in the right spot. It's checking how far away they are from the center. Now let's go work on the foci. Again, c squared is a squared minus b squared. A squared is 49 and b squared is 9. You're basically always going to do the two denominators, big minus small. 49 minus 9 is 40. And then I'm going to go ahead and take the square root on both sides. So the square root of 40 is going to be about 6.3. Now I have to add and subtract that to the x part because it's always going to be the same as the vertices. So since my center was -1, 2, I have to add and subtract 6.3 to the x part of my point. the other part of the point will stay as a 2 the whole time because you only change one of the variables. Now, -1 plus 6.3 is about 5.3, and -1 minus 5.3 is -6.3. Oops, sorry, did that wrong. Sounded a little weird. Is -7.3. So basically over 5 and a little more up to. So 1, 2, 3, 4, 5 and a little more up to 1, 2, 3, 4, 5, 6, 7 and a little more up to. Just like that. Now I was drawing those dots so you guys could see how I was counting out those points. And then the ellipse itself only gets drawn through the vertices and the co-vertices. The foci are mainly there so that you understand that those are the points where everything would sort of reflect through. I know that's slightly too big, so let me resize it. There we go. Okay, there is one more problem on the back side that I want to talk to you guys about, and that is because it does not have a 1 on the right side like it's supposed to. So you'll notice that the 2 we did over here both have 1s. I have to make that happen here, so I need it to be 1 instead of 144, which means I need to divide by 144. And remember that your calculator can simplify fractions for you, but I will just say that 144 divided by 9 is 16. So 9 divided by 144 is 1 over 16. And 144 divided by 16 is therefore 9, which we could have found out from just doing that once. I just wanted to kind of prove it to you. So they sort of just switch numbers and it becomes the denominator instead, because 144 is 9 times 16. So it's kind of like saying the 9 cancels out and the 16 is what's left. The 16 cancels out and the 9 is what's left. And that will happen every time you need to do something like this. But basically how that helps us is now I can see that my vertices are going to be 4 units away on the x-axis, and my co-vertices are going to be 3 units away on the y-axis. Simply because x has a bigger number underneath, that's going to be the longer side, so those are the vertices. The co-vertices are always shorter. Now there are no numbers on top with x and y, so my center is 0, 0. And this time, I'm going to actually find my vertices and co-vertices before I graph them. So if my vertices are 4 units away on the x-axis, that means I'm going to add and subtract 4 to just the x part. Then, to find my co-vertices, they are 3 units away on the y-axis, so I'm going to add and subtract 3 to the second value. So 0, 3, and 0, negative 3. Now, I realize that's a little trickier, so if that's not your jam, all you had to do otherwise is put the center at 0, 0, and count over 4 in both x directions. 4, 0, negative 4, 0, and up and down 3, 0, 3, 0, negative 3. And this one almost looks like a circle because they're not that far apart. There you go. Just don't forget you have to go find your foci afterwards. The foci on this one, ac squared equals a squared minus b squared. So c squared equals 16 minus 9. Because a squared is 16, b squared is 9. 16 minus 9 is 7. And the square root of 7 is about 2.6. since our vertices or the longer side is on the x-axis, that'll have to go along the x-axis. So we're going to add and subtract 2.6 to the x part of the center, which is going to give me 2.60 and negative 2.60. Since that's about negative 2.5, I'm not going to go up any at all, but I am going to go left and right about 2.5. And this time you'll notice they're a little closer to the center. They're not as squished into the vertices as the other two were. That's because this one is more circular. As an ellipse starts becoming more of a circle, those two foci points start to become the middle point or the center. So a perfectly circular ellipse would mean the foci are going to be the center and everything kind of squishes back to being even all the way around.